Hello everyone, I am Alok Kumar and today I would be doing tangent and normal. It's one of the most important applications of the concept of differentiability and we will see that it's really straightforward. So let me now share my screen with you all. So to motivate the discussion, let me start with a just statement, two statements rather. So it is given, let me read it out. It is given let f a comma b to R, where A and B are open, so they are not counted in the interval. So let f a b to R be a function, and C belong to A comma B open. That is, C is an interior point. Of course, every point is interior to the interval. So statement first is that if f is differentiable at C, then the graph of f has a tangent at C. And the next statement is that if the graph of f has a tangent at C, then f is differentiable at C. So you have to decide about the true or false, like the out of two statements, which is true, which is false. So let me tell you the answer first, and maybe by green, and then we will discuss them. That why it is happening. So the statement one that if f is differentiable at C, derivable at C, then the graph of f has a tangent at C. That is all right. That's true. That's true. Mind you, when I say differentiable at C, it means derivative exists and it is finite, means exists finitely. But the second statement that graph of f has a tangent at C, then if it's differentiable at C, that is false. So if something is false, I need to give counterexample, as I have told you earlier also. And if something is true, then of course I have to prove it. So first is a straightforward application of the concept of differentiability and the tangent line. So what we are saying is that if f prime x naught is limit h tend to 0, f of x naught plus h minus x naught over h. So we are saying that if this exists, I emphasize finitely. It's not infinity or negative infinity, or they are different from both left hand and right hand, then of course it does not exist. So if f prime x naught exists, that is the derivative at x naught exists, then this only is called the differential coefficient of f at x naught, and then this serves as m, and then we can write y minus y1 is m times x minus x1 as the equation of tangent line, tangent at point p x naught comma f of x naught to the curve. So that follows from definition, is straightforward. When you come to the second one, why it is false, that if you come to tangent, then by definition, because if this axis is finite, so this can never be infinity. But we can have a case, say, look at this one, look at this curve, this kind of thing. So you see that this line looks like a tangent to this curve, and so it is a vertical line. So for vertical line, we have got a different concept. So we will just go over it. So I'll write something called vertical tangent. Vertical tangent. So let me motivate the definition first. That if AB to R is a function and C belongs to A comma B, that is open interval. So C is an interior point. C is an interior point. In fact, every point in this interval is interior. We make this distinction because after a while I'll tell you something about the closed interval. So C belong to A comma B open, and f is a function. Now, if f is if f has a derivative at C, So it can be either left-hand derivative or right-hand derivative or both. And suppose they both are infinity, or both are negative infinity, or one is infinity, other is negative infinity. Can be like this also. So it means that if f has a derivative at c, but the derivative either both left hand and right hand, they are both infinity, or both are negative infinity, or one of the left hand or right hand derivative is plus infinity, other is negative infinity, then in all these cases we will say that f has a tangent at the point c on the curve, that is cfc. One warning, that first of all, f must be continuous, otherwise it does not make any sense. So of course you are saying rather this would come first. So f is continuous at c, and then if f has a derivative at c such that both left hand and right hand are infinity or negative infinity, or one of them infinity, other negative infinity, in all such cases we will say that f has a vertical tangent. So we will say that f, the graph of f, the graph of f has a vertical tangent at CFC. This what we will say at the point. Now some examples are in order. So let me take the example f of x is x to the 1 over 3. Now this curve, if I sketch, so let's call this 1a because there would something like 1b also will come. So fx is x to the 1 by 3. So this curve, I can draw something like this. This is like this. You may note that y, this curve is y is x to the power 1 over 3, and suppose I take the curve y equal to x cube, then these two are reflection of each other in the line y equal to x, because when this is equivalent to y cube equal to x, and so you see that change x to y, the curve change into each other, and so they are indeed reflection of each other in y equal to x line. Y equal to x cube is a much famous curve, and it particularly because it gives you a counterexample for many of the statements in calculus, so it's much celebrated. So I will this goes like this. This is y equal to x cube. It has a horizontal tangent at origin. That's not of concern here. So y equal to x cube. And if I reflect the curve in the line y equal to x line, in this line, if I reflect the curve, let me change a new color. So I will get this kind of thing, roughly this kind of thing. And this, you see that this is what we have drawn. So this is y equal to x cube. This was the green color, and this is nothing but x equal to y cube. That is, I wrote y is x to the power 1 over 3. So this anyways important curve, so students should make a particular note of it. They will come to haunt you always, y equal to x cube. And it's a beautiful curve because they will give counterexample to many of their statements in calculus, worth knowing. Okay, so back here. So let me change the color one more time in green. So fx is this, and I want to investigate that at x equal to 0, what kind of tangent it has. So apply definition. F prime plus 0 means right hand derivative at 0 is limit of h tend to 0, f of 0 plus h minus f of 0 over h. This further rewrites as limit of h tend to 0. Remember, f of x was this one, x to the power 1 over 3. So you have got h to the power 1 over 3, and this is 0, so upon h. So limit h tend to 0, 1 over h to the power 2 by 3. And this limit we know does not exist, and of course we are perfectly justified in writing equal to infinity. I have remarked in earlier lectures also, when you say equally, when I write limit x tend to something a f of x equal to infinity or negative infinity, don't think it's a real number. The sign of equality is just the notation. It's just the notation. It does not tell you that something becomes a real number. Or you say this way, it just tells you that as x approaches a, the limit of f at as x approaches a tends to infinity. Means as x tends to a, fx tends to infinity or negative infinity, means that as x gets closer and closer to a, the values of fx get larger and larger than any positive number you can think of, or values of fx get smaller and smaller than any negative number you can think of. So these two are your conceptual things. Now, so we see that f prime plus 0, that does not exist. That is in fact infinity. So this function has a positive infinity derivative to the right side. Let's do the same thing with left derivative. This is by notation f prime minus 0, and that definition reads limit h tend to 0, f of 0 minus h minus f of 0 upon negative h, and that gives you limit h tend to 0, f of minus h. So again, you are back to minus h to the power thus minus 0 upon minus h. Minus comes out, this is 1 over 3. So this is limit h tend to 0, h over 1 over 3 over h. This still is limit h tend to 0, 1 over h to the power 2 by 3. As before, this also gives you infinity. Means what you have got is that left and right. So f prime plus 0 and f prime negative 0, this is infinity, this also is infinity. This is right hand derivative and left hand derivative. And so, although f is not differentiable at origin, because being differentiable means that derivative must exist finitely. So f is not differentiable. F is not differentiable, not derivable. F is not differentiable at origin, but our definition says that if function f has an infinite derivative or negative infinite derivative or one of them, then also f will be said to have, or f will be said to possess a vertical tangent at the point C. And so I will say that this line, the line x equal to 0, is a vertical tangent to the curve at origin. So that's plain example. You are getting this one. Similarly, if I consider f of x is negative x and 1 over 3, the same example you will find now that f prime plus 0 becomes negative infinity and f prime negative 0 becomes negative infinity. And so the function is still, this function is still has a vertical tangent at origin. So we discussed 4 of the cases. So both infinity, both LHD and RHD, both negative infinity, and one of them positive infinity, one negative, or other way around. So this thing we are doing. And so let's take a second example, 2a. So this tells that I'll quickly change the example, and fx is x to the power 2 over 3. And this function, if I graph it, again, this is defined. So if I graph it, it will come like this. So we will once again find at origin, looks like this is going to be a tangent. Let's confirm what our theory says, what our fundamentals say. So f prime plus 0 by definition is limit h tend to 0, f of 0 plus h, f of 0 over h. So limit h tend to 0, f of h minus f of 0 over h. So limit h tend to 0, f of h Obviously, this is h to the power 2 over 3. f0 is 0 over h. That gives you limit h tend to 0, 1 over h to the power 1 over 3. And this number, if you say h over 1 over 3, then this limit is infinity. H is always positive. Okay, now if I take f prime minus 0, that is, this was right hand derivative, this is left hand derivative. So that gives you limit h tend to 0, f of 0 minus h minus f of 0 upon negative h. This is the same difference in the same order. So negative h, don't forget. Limit h tend to 0, f of negative of h minus f of 0 upon negative h. So limit h tend to 0, f of negative h, and that becomes negative h whole to the power 2 over 3 and upon negative h. Here there is something change. Limit h tend to 0, this still is h to the power 2 over 3 because minus 1 to the 2 over 3 I can deal in two ways. One, I can write minus 1 whole to the power 2 and 1 over 3. That will give you 1. 1 over 3 is 1, or minus 1 to the power 1 over 3 cube root and 2 squared. So that will be minus 1 squared, so still 1. That's important. So we get this one, but in the denominator you have got negative of h. And so compare the previous one. You have got here limit h tend to 0, negative of 1 over h to the power 1 over 3. So this number was positive here. The sign in front of it is no sign, so positive. Here sign is negative, and that results in saying that this limit is negative infinity. So although f prime plus 0 is not f prime minus 0, and of course this is plus infinity, and this number is negative infinity, still we know by our definition that this f, the graph of f, has a vertical tangent at origin, that is x equal to 0 is a tangent or is the tangent to the curve at origin. So we have got all three vertical tangents. Let me change a color in, let me change the color in, say this way, that so this is okay, this color might be okay. So we are saying that this line, this line, this line, this line is a tangent, vertical tangent. If you come to the next example, this also is the same, and here this line is a vertical tangent. Although there is some there is some name for this one, but then we don't go into it as this is not in JEE syllabus. So next we will just look at, before remarking, that if I take other case like twice b 2b, then I'll just change and I will write f of x equals, this was x to the power 2 over 3. I can write f of x is negative of x to the 2 over 3. Now this time the right hand derivative will tend to negative infinity and left hand derivative will tend to plus infinity. And so we have covered all four possible cases of right hand derivative and left hand derivative. And so I told you that earlier also, that positive, this is both, this one, both positive, both negative, one positive, one negative. So these four cases we have covered. And now we are saying in each of the cases, provided f is continuous at C, we will say that f indeed has a vertical tangent. So all these curves has a vertical tangent at origin. Okay, one more example of the same kind, but little different. So this is, what about this curve? F of x is square root of x. Obviously, when you are given this curve and investigate at origin, investigate for say tangent. So what I will do, first I know that this domain of f, so domain of f is 0, including infinity. So this is all numbers. It is defined for all non-negative reals thanks to the radical sign, the square root sign sitting over here. So fx is square root of x. That domain is non-negative real numbers. Now, to find f prime 0, if someone asks you f prime 0, then because this function is defined only on the right side of 0, so f prime 0 will be taken to mean f prime plus 0. F prime negative 0, f prime negative, let me erase this. So f prime negative 0 does not make sense. This is meaningless. So we are happy, we are content to find just f prime plus 0, and this only will be the derivative of f at 0. So if I write that f prime plus 0, so f prime 0 equals f prime 0 plus 0, that is limit h tend to 0, f of 0 plus h minus f of 0 over h. That gives you limit of h tend to 0, f of h, f of 0 over h. That gives you limit h tend to 0. This is square root of h minus 0 upon h. So limit h tend to 0, 1 over square root of h. And you can clearly see as before that even this limit does not exist. It just blows up. So this is, of course, plus infinity. So here also, f is not differentiable at origin. In fact, what it is called that f has an infinite derivative at x equal to 0. And so by definition, graph of f has a vertical tangent at x equal to 0 origin. That is the line x equal to 0 is the tangent to the curve at origin. So we have seen in all cases here also, if I draw the graph, this curve looks like this one. And so here also this line, here also say this line, change the same color, we probably. So here also this line, this is again x equal to 0. This line is a vertical tangent to this curve. The curve does not exist. This here say this side, the curve does not exist. That does not mean it cannot have a tangent, because we are applying the concept of what is called, we are applying here one-sided differentiability. Just like we did one-sided continuity. And of course, note that f is continuous at origin, because f is continuous at origin. I'll do here only f is continuous at origin, because if you write f of 0 equals 0, and f 0 plus, that is left hand limit, that is LH, that is or HL, I'm sorry about that. That is right hand limit f 0 plus is still root of limit h tend to 0 h, that is still 0. So if it is of course continuous, you can see the graph also, that f, of course, you can draw the graph of f without lifting your pen off the paper, and geometrically that makes sense. So in all these cases, we have learned that if f is continuous at a point C, and even if f has no derivative, like derivative is infinity or negative infinity, or one is infinity, one is negative infinity, still in those cases, f will have a tangent, vertical tangent at that point. So let me go back to a discussion that is started. And so this statement, the statement we started the class with, so first is obviously true that if f is differentiable, at C, then graph is tangent at C, perfect. But if the graph of f has a tangent at c, then f must be differentiable. That's too much to ask, because for a vertical tangent, by definition, you will find that derivative is infinity, and of course, infinity does not exist. And so we have got this statement that's false. Hope that clears it. Let us move to the next one. So let me change the color perhaps, and let me do a problem to illustrate. Rather, first let me tell you the remark that I made continuity. So this is the warning. So it's in red. So warning is this, that suppose we have got a function like f of x is, say, signum x, it is called, but not mysterious. It's just 1 if x is positive. It's 0 when x is 0, and negative 1 when x less than 0. So the graph looks like at 0 it is 0, so it is x equal to 0, it is 0. When x is positive, it is 1. So it is start whole from here, positive it is 1. When x is negative, it's negative 1. And so again, this is a whole, and it goes like this. Obviously, f is not continuous at origin. We can just quickly check it, although it is obvious. F0 plus notation means right hand limit of f at 0. F0 plus is limit h tend to 0, f of 0 plus h, limit h tend to 0, f of h. And if h is positive, h tend to 0, this goes to 1, so that's 1. So that limit h to 0, 1. And if I come to left hand limit, notation is f of 0 minus, and limit h tend to 0, f of 0 minus h. So limit h tend to 0, f of negative h. When you are on the negative side, so this is negative, so that number is nothing but limit h tend to 0. This whole thing is negative 1, constant, and so limit is 1. The way it was limit h tend to 0 positive 1, so, and does not depend on h, so this is 1. So it means this is this kind of thing. So they are not equal. So anyway, limit does not exist, and so there is no question of continuity. Although f0 is defined, that does not matter while calculating limit. But f0 on record, f0 is defined to be 0. So we know that this function is not continuous. Although if I calculate f prime plus 0, by definition, it is limit h tend to 0, f of 0 plus h minus of 0 over h, and that gives you limit h tend to 0, f of h minus f of 0 is 0 over h. So limit h tend to 0, this is 1 over h, and this 1 over h we know is infinity, plus infinity, positive infinity. And if I get f prime negative 0, that is limit h tend to 0, f of 0 minus h minus f of 0 upon negative h, and that means limit h tend to 0, f of minus h minus 0 upon negative h, limit h tend to 0, f of negative h. Now that number is negative of 1 upon negative of h. It's a still limit h tend to 0, 1 over h, and that gives you infinity. So although the function has an infinite derivative at origin, it does not have a tangent there because f is not continuous at origin. In fact, if f is not continuous at origin, as you can see, there is no sense, there is no meaning in finding a tangent at that point. The point only is not there. Okay, so this was about the definition, complete definition of tangent and normal. Not normal, this tangent. So once tangent is there, normal, of course, we know is a line perpendicular to the tangent and passing to the same point. So that's easy to find. Okay, let me do one problem quickly, which tells you some other aspect. So like this one. Say we have got, say there are 2 points, say points A, point A is 5 minus 2, and B is 0, comma 3. So we have got some point, and say curve is there, y is x upon k plus 1. So my question is this. Your question is find k such that line AB is tangent to the curve, tangent to the curve y equal to x over k plus 1. Now I'll make use of simple things. We can graph the function. Let's it's not this, just a moment, let me write again. This is y is k over x plus 1. It's y is k over x plus 1. So let me change it here also. So this is about not that. So y is, make this correction, k over x plus 1. So in fact you want the value of k, element of R of course, such that the line AB becomes a tangent to the curve y equal to k over x plus 1. Now one can draw the graph of y equal to k by x plus 1, but it does not matter. Let me just, for the sake of completeness, do it. So y equal to x curve, y equal to 1 over x, y equal to 1 over x. This curve goes like this. Now if you talk of y equal to 1 over x plus 1, then this just changes. So this line is x equal to -1, and so this becomes our new axis. These ones, like say these ones, this is my new axis, these two. And so my graph, if I write my graph, then this becomes, so this becomes like this and like this. And so I need not draw it perfectly. Here I can just say that, okay, there is some line. The points are, this is point A, that is 5, -2, and point B, that is, so that is A is 5, and so A is here, somewhere here, A. Okay, and then this B is 0, 3. So suffice it to say that you have got some line here and some curve you want, some curve. So some curve, that curve name is y is k over x plus 1. That's the how it is defined. And this line AB is there. We want to find when this line is a tangent to this curve. So first find the equation of line. So this line is A 5, -2 and B 0, 3. So I can find the slope of line AB. So that is 3 minus -2 upon 0 minus 5. That is 5 for -5, so -1. So my equation of line is x plus y, because slope is -1. It's some constant. And because the line passes through any 0, 3, so this is 0 plus 3. So I will write x plus y equal to 3. So this line becomes x plus y equal to 3. So this line is the equation of the line AB. And then you want some k such that this line is a tangent to this curve. So in effect, what I'll do is that this is some curve 1, this is line 2. I will intersect 1 and 2. So let us find the solution of y equal to k over x plus 1 and x plus y and x plus y equal to 3. If you solve them simultaneously, both same at a time, simultaneously, then you expect to get some answer. So that will tell you how they're intersecting. So I'll plug in the values. So you have got y is k over x plus 1. So I can write y is 3 minus x is k over x plus 1. If I multiply, I'll get 3 minus x times x plus 1 equal to k, that is negative x squared, and this is 3x minus x, that is 2x, and then plus 3, that equals k. So that gives negative x squared plus 2x plus 3 minus k equals 0. Now one important point. If you have got ax squared plus bx plus c equal to 0, and you want roots to be equal, then the condition is that discriminant b squared minus 4ac, that must be 0. So what we will do, that we will say like this: because we know that this line is a tangent, this line, because you know that the curve and the line touch each other, it means that uh, algebraically this point, say this point coordinate is alpha and this is alpha beta, then when you solve, in alpha we should get alpha repeated twice, that makes sense because it is tangent, and so we expect that there should be two values corresponding to it. If you get different values, it means that this line intersect, because this line can meet the curve either exactly in one point, means two coincident points, or two distinct points, which is not possible because you want it to be tangent. And so the condition is that discriminant must be 0, giving b squared minus 4 ac is 0, that is 4, and plus 4 times 3 minus k is 0, that is 1 plus 3 minus k is 0. So that gives you k equals 4. And so you have found that if the curve is y equal to k by x plus 1, that is y equal to 4 by x plus 1, then this curve will have this line as a tangent. You can also find the point of tangency because x value is known. The x value from here, x value, is just minus b over 2a, although somebody can do minus x squared plus 2x, and k is 4, so that is negative 1 is 0, and so you will get x squared minus 2x plus 1 is 0, that is whole square is 0, so you're getting 1 and 1. That tells you repeated root, that indeed at x equal to 1 there is a point of tangency. So the point on the curve, the point of tangency is x is 1, and because y was 3 minus x, so y is 2. Or no need to do this, no need to solve. Go back here, because you know k value is all right, because you know that it is a point of tangency, it means that this discriminant is 0, and so x value x naught should be negative of b over 2a, so that is negative of b, that your b happens to be 2, and this is 2 into a happens to be negative of 1, and so we are done. X naught is again 1, and once x naught is 1, we get y naught, that is 3 minus x naught, that's 2. So we have done this problem, that finding k such that some line, given line, becomes tangent to the given curve. So find that k. Let me take up the other example. Say, so now a similar question, but little tricky, that this is tangent at, suppose there is a curve y equal to x cube. I just drew it before, y equal to x cube. Now the tangent at p 2, 8 to the curve meets the curve again at q, say q, then find q, means find the point. So the question is, tangent at point 2 comma 8, so tangent at point 2 comma 8, so 2 comma 8, this is 2 comma 8, tangent at P meets the curve again at Q. You want to find what Q is given 2 and 8 and the curve. It's an application of the tangent and normal chapter. So we'll start like this, that first of all, I'll find the tangent at 2. So curve is y equal to x cube. This curve is given. So dy over dx is 3x squared. So dy by dx as the point x equal to 3, x equal to 2, this point happens to be 3 times 2 square, that's 12. So it means we got y equal to this slope. We get this slope of the tangent is 12. And so I can write equation of the tangent as 12x minus y is some constant c. And this I can get because there is a point on the curve, say 2 comma 8. So 12 into 2 minus 8. So this is 24 minus 8, that gives you 16. And so we have got 12x minus y minus 16 equal to 0 is the tangent to the curve y equal to x cube at P 2 comma 8. This was the first step, getting equation of tangent. Now, already curve is here. So now I just want to solve tangent and the curve. So I just want to solve this curve with this tangent to find how it meets. I did not even draw the diagram. In JEE Advanced or other thing where you have no time, you have to determine what kind of diagram you want to do. A rough diagram will work or even no diagram. I recommend you just make a rough diagram so that things are in clear focus. So this is the tangent of the curve. Now you have to solve. You have to solve these two, solve them simultaneously, both at a time. So you have to solve them simultaneously means that just plug in anything, say y looks good. So I'll write y is 12x minus 16, that is x cube. And so x cube minus 12x plus 16 is 0. So we get this one. Let's call it some polynomial. So let's call it polynomial a of x, polynomial. We have to find the roots of it. You know, for a simple polynomial cubic, all you do is start by finding integer roots. And you know that if root is integer, then the root must divide the constant term. So we check that divisors of 16, 1 of course does not work. If you check 2, then you find a2 is 2 cube minus 12 into 2 plus 16. So that is 8 minus 24 plus 16. Good, we are getting 0. So in fact, 2 is a root. So we found 2 is a root. That's all right. We need not find another. So we can write x cube minus 12x plus 16 as x minus 2 times. Now, often students divide this now. They divide or they pair up or they do the long division. I don't recommend. You now fix the coefficient of the highest term and lowest term. So this is x over here, x cube. You must have x squared here. Coefficient, this must be 1. Because x cube can be obtained only by multiplying x squared and x. Then here something ax, I don't know. And this number must be negative 8 because the 16 can come only by multiplying the last two terms minus 3 and this coefficient. So that must be negative of 8. Now I'm left with a. So just equate coefficient of x squared on both sides. Say x squared coefficient is 0 here. Here x squared coefficient from x, it will be a. Here it is minus 2. So a equals 2. You could have also done coefficient of x. So minus 12. This is enough, but just to show you, minus 12. X coefficient, here it is negative of 8. And here ax, so this minus 2 will give minus 2a. Giving you 2a is 12 minus 8, 4. So again, a is 2 as expected. So it means we have quickly found that x cube minus 12x plus 16 equals x minus 2 and x squared plus 2x minus 8. This again factors and we can write quickly x plus 4x minus 2. You can check P2 is 0. So it becomes x minus 2 squared times x plus 4. And so 2 already is there. So you got a new root, x is negative of 4. And so y is x cubed, that is minus 64. And so if you tell them, you can find that your point q is negative 4, negative 64. This is the point q. So we have found by solving that if the tangent at p meets the curve again at q, then the q point happens to be negative 4, negative 64. By the way, that is shortcut, and that's elegant. Remember or notice that when we solved it, we found two roots. We found 2, 2, and negative 4. Don't you think why this repeat 2 and 2? That is a story. So if you are solving a curve, say in this case this was the curve, some kind of thing, and you are solving this line with this curve. So in fact, this line is of degree 1, of course linear. So this is degree 1. This was degree 3, y equal to x cube to be precise. So if you solve some ax plus by plus c to some cubic, say x cube and something, y equal to x cube or fx cube, then here x cube. So what will happen is that you will get a cubic in x. Now that cubic will have 3 roots. Now intersection points are p and q. If roots are distinct, it means this line meets the curve in 3 different points. That's not possible, you see. And anyway, p, you have got at p, it is meeting like tangent. So corresponding to this value, x should be repeated. So it means the moment we reach the equation here, I'll write it here, x cube minus 12x plus 16 equal to 0. It is a cubic which will have its roots for xp and x cube. We already know that xp should give rise to, x was here 2. So you will find here that it should give rise to 2 and 2, and third should correspond to x cube. So I can just use product of roots. So 2 into 2 times x cube is product of root, that is negative of 16, and that gives you x cube is negative 4, same as you got before, as you should get, same as before you get. So that's really nice. So you are getting this statement that okay, x cube is also equal to negative of 4. So these kind of things really work wonder. So please watch out for this. So whenever you have got something tangent, remember that this root, when you solve, this would occur twice, and then you can use product of roots to find the remaining third root. Okay, there is one more approach. There is one more approach in, say, second solution. You will do like this, that this is y equal to x cube, and this point was of course 2, 8. This is p. We'll find it useful. So let me write and give it a name. It is called parametric form. Means first you are getting a parameter for the curve. Now parametric equations for a curve are not unique. Means you can have many different parameters. For example, x squared y squared equal to 1. This is the famous circle. So one parameter is that xt is cos of t, yt is sine of t. Of course, you can assign some t such that it takes care of all the things. So we can go from 0 less than t less than 2 pi to take care of all the numbers. So this can be taken care of. So this is your xt and yt. So this also is one thing. Notice this. Suppose somebody writes x as 1 minus u squared upon 1 plus u squared, and y is 2u upon 1 plus u squared. That's a little tricky, but just check 1 minus u squared over 1 plus u squared whole square plus 2u upon 1 plus u squared whole square. You will get in the denominator 1 plus u squared whole square. Numerator is 1 minus u squared whole square plus 4u squared. Now this is a minus b whole square plus 4ab, that equals a plus b whole square. You will get 1 plus u squared whole square over this one, same thing, so it becomes 1. So you find that even this also is a parameter. X is x cube, u is the parameter, y is y of u. So these two are parameter. So these parameters are different. One looks algebraic, other looks trigonometric. Of course, we can reconcile them. If you remember your trigonometry well, if you remember these results, that 1 minus cos squared theta, 1 minus, not cos squared, 1 minus tan squared. So 1 minus tan squared theta upon 1 plus tan squared theta, that is equal to cos of 2 theta, and sine of 2 theta is 2 tan theta upon 1 plus tan squared theta. You will find why they both make sense. These both are actually same, but still written differently. And so we say that the parameter need not be unique. They are not unique. For our case, come back here. For our case, we can take the parameter as t cube. So any point P I will represent as t cube here, because point is 2, 8. So t is 2 and t cube is 8. Both give simultaneously t equal to 2. So 2 is the parameter t value corresponding to point P. So I model my question now like this, that you have got. So I model my question like this, that you have got here now some point P, that is, call it T, and some tangent, and it should meet at, say, Q. So Q I will write as capital T. Mind you, T is given, a small t is given. Say here T equals 2, and I want to find T. So I can do like this. This is the method MPQ, slope of tangent. I can write as this. T full name is t cube. So, and this is t and capital T cube. I can write t cube minus t cube over t minus t. As t is not t, I can get t squared plus tt plus t squared. That will work. So that is your, this one, PQ. That is slope of line PQ. And also, I can find slope of line PQ as tangent to the curve at P. And that slope is dy over dx at point P. That is by parameter d over dt over dx over dt. So dy dt over dx dt, and dy dt is by this one. Already we saw x was t, y is t cube. That is 3t squared over t. So that is 3t. This is just 1. So this is this. Let me erase this so you can have. Yeah, that's good. 3t squared upon 1. So that is 3t squared. So we find that this is there, and these two must be equal because they're the same line. So t squared plus tt plus t squared is 3t squared. That gives you t squared plus t times t minus 2t squared is 0. So now we see that given t I want to find, I want to find t in terms of capital T in terms of small t. That is t as a function of t. I could have, of course, put t equal to something, that given t equal to here 2, but I want to prolong it, and I want to see you postpone, and in the last step I want to write possibly. So here again you will find this will factor, so you will get t plus 2t and time t minus t, that equals 0. So you will get t equal to t, or t equal to negative t. T equal to t, of course, corresponds to point P. So this must be Q. So you get t equal to negative of 2t. and negative 2t. So let's now put what t was. So my TP was 2 initially. So my t corresponding to q is minus 2 times 2, that is negative of 4. And so the point x and y, q point, so x is t and y is t cube. So that gives you now x is t cube. This is negative of 4, negative of 4 cube. So my point q becomes negative of 4, negative of 64. So that is one answer. So we get this kind of thing, negative 4, negative 64. So we have solved the question that given a point, given a point P on the curve on which we draw some tangent where it meets. We can apply this anywhere. Say you have got some curve which you don't know the shape also. So from some point P, you are drawing a tangent. Depending on degree of curve, it may meet at more than one point. So say Q or S. So this is T. You designate one of them as small capital T, and your job should be to find T in terms of T. And you note that this equation in T, must have double roots T and T, and that will shorten your work. You can quickly get to the point. So that's you will get here. Okay, same observation. Let me change the color one more time. In same observation as we made last time, is this, that we need not solve again this one. We have got t square plus tt minus 2t square is 0. Now, if you remember it, this curve is this. Of course, this is here. So this kind of thing is there. Now, so this p, we know that this p corresponds to a small t, and we expect values of t. But then this is q. You expect only one value of t that would correspond to point q. So we already know t is there. So this quadratic we know has a root. T must be there because already one t was deleted. So t must be there here. So this is t. And then mind you, here not tt because this degree is just 2 now. Degree is 2. So it means here only 1. So once t must come because already t once came here. If you remember, we cancelled here. We cancelled here in the formation of this one. T, this is t minus t here cancelled. T minus t. So one t is already gone. So one t is here, small t. So this is small t here. Product of roots t times, so write tq and times t, that equals to p. And that equals to negative 2t squared. So tq is nothing but negative 2t. So I need not solve this. I can just claim by knowing that the roots at the tangent must be multiple root of order 2 at any point of tangency. And so I can quickly say tq is negative of 2t. And once I say negative of 2t, then we get the same thing. We are back to our first solution, which of course give you negative 2t. And then the point as happens is minus 4 minus 64. So from these examples, we learned that how to creatively use the definition. And it's after calculus, next step is just algebra. And we are trying to find out that given a curve and then some tangent to it at P where it meets again at Q. So that's all for today. Let me go back in the screen. So that's all for today. Let's meet tomorrow again. Have a good day.